Intel has always been really good at R&D. Furthermore, all throughout their history, they've had the balls to take swings on new technologies. The high-K metal gate, the FinFET transistor, strained silicon engineering. Doing these innovations took guts. For all of their struggles, Intel never lost that, and their coming 18A node is going to be another one of those big Hack-Wilson type swings. One of the two bold innovations in that node is the gate-all-around transistor, which I covered in another video. The other innovation is not as sexy, but I argue is way more electric. In this video, let us look at Intel's next breakthrough, the backside power delivery network, or as I shall insist on calling it in this video, BSPN. But first, this video is brought to you by the Asianometry Patreon. Early access members get to see new videos first, and selected references for those videos. Early access really helps me a lot, and I appreciate every pledge. Thank you, and on with the show. I'm going to do my best here, but this stuff is particularly tricky, so forgive me my errors. Before we begin, I want to recommend Doug O'Loughlin's 2 write-ups on this topic. Doug is great, and he did very well here. Feel free to read it first before you move on. I also want to point you guys to the research done by IMEC over in Belgium. They pioneered the technologies behind BSPN and have published loads of material about it. Let us start with the basics and then work our way up. The core function of the transistor is to switch on or off upon the receipt of a control signal. In order to do that, they need power stably supplied to them at the right voltage. Power is the measure of doing work, as in how quickly energy is being used. Mathematically, it is current multiplied by voltage. Voltage is the force that drives electrons through wires, like the pressure that pushes water through pipes. If the voltage is too low, then the transistor might not switch properly. Think of opening a water pipe and finding no water because the pressure isn't there. A 1% drop in gate voltage results in a 1% decline in the chip's operating frequency. At its worst, insufficient voltage can cause timing errors, which in turn cause a blue screen of death. But if the voltage is too high, then the chip starts using too much power. The power consumption of a switching circuit is proportional to the square of the voltage. Higher voltage, more power consumed. And if the voltage gets way too high, then the transistor's gate oxide might break down entirely from the powerful electric field. The voltage at which this happens is sometimes called the reliability wall. We should take care to avoid breaching it. Different sections of the integrated circuit have different voltage requirements. Designers segment the chip into areas called power domains. Some mobile SoCs might have hundreds of power domains to best optimize power usage. Thusly, delivering power is a Goldilocks situation. Not too little, not too much, just right, within a margin of about 5 to 10%. And it has to be delivered stably, efficiently, and reliably. Think of a desktop CPU. Where does its power come from? It comes from the power supply, which provides a high voltage and current to the CPU through the sockets and socket pins attaching it to the motherboard. If we're talking about mobile chips rather than a desktop CPU, then we won't have socket pins, but rather solder balls. Pins are too big. Once it enters the chip, power must travel through the chip's packaging to the transistors. This is done using a customized network of metal wires or interconnects and vias running throughout the chip. Vias help us go between the IC's many layers. So think of interconnects as being like roads and vias as like Mario pipes. There are 2 other devices spread throughout the system: voltage regulator modules and decoupling capacitors. First, voltage regulator modules. The IC's various power domains have different needs, so the voltage regulator modules step the voltage up or down as needed for each domain. Voltage regulator modules are nice, but sometimes cannot leap into action fast enough. So we add decoupling capacitors to smooth out the network. Like, if a microprocessor suddenly ramps up for something, the sudden activity may cause voltage spikes via inductance in the metal interconnects. Inductance refers to the fact that when a current flows through a metal interconnect, it produces a magnetic field. If we're to change the current, like if we turn it on or off, then that interacts with the magnetic field in such a way to create unexpected fluctuations in the voltage. When that happens, the excess charge can be routed to a decoupling capacitor and stored for future use, like in the case of a voltage dip. So in some ways, you can think of them like drainage ponds, taking on water during the storm. And like such ponds, they are strategically placed on the PCB and even on the chip itself. Together, we call this system the power supply, the interconnects, the voltage regulator modules, and the decoupling capacitors, the power delivery network, or PDN. Much of our focus for this video is just on the interconnects, but I wanted to be complete. The power delivery network's role is to distribute power and voltage while keeping noise at the minimum. It is extremely complicated. Because we are living in reality and not in ideal simulation, metal wires suffer from parasitic inductance and resistance. Let's break that down. Parasitic, meaning that we don't want it. Like that one roommate who eats all the chicken nuggets, doesn't do the dishes, and just plays video games all day. I'm talking about you, Jeff. I still remember. Anyway, I already talked about inductance, so let's talk about resistance. Resistance impedes the flow of electrons through the metal. The result is voltage at the end of the wires is lower than what it is at the power supply at the start of the wires, kind of like how a dam holds back water. People in the industry call this IR drop, and it is one of the more serious issues plaguing the leading-edge semiconductor industry. Throughout semiconductor history, the metal interconnects carrying power sat on top of the transistors. So if you can imagine the silicon wafer, the transistors are built into the surface of the silicon. Then we use deposition, lithography, and etch to add many layers of interconnects and vias on top of that, maybe 10 to 20. The power delivery network brings power from the global power supply in from the top, traveling out and down to the transistors on the bottom. The deeper you go, the smaller the wires get. This arrangement is referred to as the frontside power network, and it worked fine for a long time. But as Moore's law progressed, we crammed more transistors together onto a single IC. Nowadays, we are dealing with billions of transistors. Since each of these transistors have to be powered, we had to add more layers of interconnects. These power-carrying interconnects interfere with those interconnects carrying electrical signals. The only way to deal with that is to make them thinner. But nowadays, these interconnects are around 20 nanometers in diameter. This results in substantial IR drops by the time the power gets through this long journey from the power supply to the transistors. Resistance is a problem that the industry has been working with for a while. It was one of the reasons we moved from aluminum to copper interconnects 20 years ago. But that was 20 years ago, and now we are beyond the 5 nanometer generation of process nodes, and these challenges have come back like the measles. At 20 nanometers, copper isn't the best metal to use, despite having the lowest bulk resistance. Copper's bulk resistivity is really good, 1.664 microohms per centimeter. But electrons traveling through it are more likely to deflect and scatter, instead of going in a straight, uninterrupted path, or as they say, electron mean-free path. So at 20 nanometers, the electrons in a copper interconnect are more likely to scatter, making its resistance higher than what other metal lines might have. Weird how nanoscale stuff works, right? Furthermore, copper interconnects require barrier layers to prevent the copper from poisoning the silicon. Those liners are generally made from tantalum nitride, which has a very high resistance and does not scale down very well. So chip designers have had to trade off signal resources in order to guarantee a more robust power system. In response, the esteemed Semiconductor Research Center IMEC out in Belgium proposed a set of new innovations, buried power rails, and then after that, BSPN. Let's do the first one first. While there have been a lot of innovations on top of the silicon surface and its transistors, there's not been as much work done beneath the silicon. This is where buried power rails come into play. We build chip designs from groups of FinFET transistors called standard cells. Power rails are what we call the strips of metal interconnects at the lowest levels, bringing power to the adjacent rows of transistors within the standard cells. We measure standard cells in units we call tracks. Your average standard cell at the 3 nanometer node generation is about 6 tracks high. But due to the issues we talked about, the rails no longer scale. They now take up 2 of the tracks, leaving the whole standard cell a bit cramped. So what IMEC is proposing with buried power rails is that we dig trenches into the silicon substrate using a methodology called shallow trench isolation. We then use atomic layer deposition to put metals for the rails into the trench. We're doing all this in the same stage as when we make the transistors, known as the front end of the line, or FEOL. The temperatures in this stage get way too hot for copper metal. So we have to use a sturdier, more thermal-resistant metal like tungsten or ruthenium. This brings upsides and downsides, as is always the case in life. One upside is that, when taking into consideration the line widths of 20 nanometers, tungsten or ruthenium metal power lines have substantially lower resistance than copper lines, for the reasons we talked about earlier, the scattering and all. So tungsten or ruthenium. The supply chain situation for tungsten is quite good, and ruthenium, for its part, doesn't need a thick metal barrier layer, only a small layer to adhere it to the surface. That's good. The downside, of course, is that fabs have never done metallization work in the front end of the line. There are metal contamination issues to consider, which always makes people nervous. After we finish cutting out and filling the rails, we can then build vias to bring down power from the larger power delivery network to the rails. Voila! We just stuffed some stuff under the floor. IMEC positioned buried power rails as the first tiny step forward in making better use of the space underneath the silicon transistors. With BSPN, we take a great leap forward. Okay, maybe let's not use that phrase. With buried power rails, the power still has to make its way down the IC's 10 to 20 layers to the silicon transistor layer. The distance gives more opportunity for metal resistance to do its insidious thing. So the bold thing that BSPN does is separate all the interconnects carrying power from those carrying signals, and then move that underneath the silicon transistor layer. To connect the network to the power rails, we dig nano through silicon vias through the silicon wafers. This is BSPN, and together with buried power rails, it cuts down on overall power consumption. How much? A study at the University of Texas, Austin, found that power consumption is about 8% better with BSPN over a standard frontside power delivery network. More critically, IR drop is significantly reduced to about 15% of that from the frontside configuration. ARM presented simulation results back in 2019 showing something similar, a 7x improvement. There are knock-on benefits too. Moving out the power interconnects lets us spread out the signaling interconnects on the top side. More space cuts down on their parasitic capacitance, unwanted stored charge that hinders their signaling speed. The idea has been pioneered in CMOS image sensors with their backside illumination system. A CMOS image sensor works like an eyeball. Light first enters through the lens and some color filters, then hits an array of silicon photodiodes built into the substrate, the silicon wafer. The more light that hits the photodiodes, the better. But with early image sensors, the light had to first pass through a mass of transistors and wiring before hitting the substrate photodetector array. This was because they built that wiring on top of the substrate. This messed with light collection, hurting low light imaging performance. So in 2009, the image sensor companies Omnivision and Sony Semiconductor Solutions announced backside illumination. They moved the wiring to behind the photodiode substrate, making it so that the photodiodes are illuminated from behind, ergo the name. This required changes in the fabrication process. I won't cover all the changes in this brief overview, but here it goes. After Sony makes the photodiodes on the wafer as normal, they then bond on another wafer on top of it. They then flip it over and thin the wafer with the diodes down to a uniform 5 to 10 micrometers thick to expose the photodiodes' backsides. Getting that exact width uniformly across the whole wafer is very hard. Sony basically grinds it down with a grinder sourced from the Japanese company Disco. I like their name. Any failures would ruin that wafer, which would be especially painful since you already did the work of making the photodiodes. Sony first released these products into commercial production with the iPhone 4 in 2010, and they have advanced the technology further with more wafer-stacked 3D sensors. Sony has shown that the concept is possible. It can be done, but what IMEC is proposing has some tricky new things to it. Rather than 5 to 10 micrometers that Sony did, we need to thin out the silicon wafers to 500 nanometers, or just 0.5 micrometers. This is way far beyond what Sony was doing 15 years ago. You start with an ordinary wafer. Then you grow 2 layers on top of it, a 50 nanometer thick layer of silicon germanium, and then a second, thicker capping layer of very pure silicon. This capping layer is where we then cut our buried power rails using the aforementioned shallow trench isolation technique. We also use ALD here to metallize the trench with tungsten or ruthenium. Then we bond on another wafer on top of all of this. This is called the carrier wafer, because we are going to flip it like Sony did. The carrier wafer, at first bonded on top, is now on the bottom. We then grind down the original wafer's backside in a series of steps. First, we use a grinder, then a polisher, and then finally semiconductor etching tools like dry etch and wet etch. Last is the wet etch, which involves applying acid to eat away the aforementioned silicon germanium layer and exposing the very flat capping layer. We are now ready to dig the through silicon vias into the silicon layers to connect the buried power rails to the power network. IMEC used lithography to tell the etch machines where to dig the vias. Then we use etch to dig the TSVs where the lithography patterning tells us. IMEC used a type of etch called the Bosch process. It works kind of like atomic layer deposition in that it works via an alternating 2-step cycle. First, we fire a plasma of acid gas to etch the silicon, then we fire a Teflon chemical to deactivate the etch and keep it under tight control. This cycle eventually drills the TSV, which is about 90 nanometers or so wide. We then clean the TSV, line it with a barrier, and then metallize it with copper to wire it to the greater power network. IMEC has laid out the overall process, and it seems like all the fabs will largely follow it. What the fabs need to decide is on the finer details, tungsten or ruthenium, the width of the TSVs, what liners to use, and so on. Intel calls their version of BSPN Power VIA, and it first entered their process flow with the 20A process node, which precedes 18A. TSMC will have BSPN 2, but are more conservative in its introduction. Their N2 node in 2025 introduces the new GAFET transistor. They reserve BSPN for a follow-up N2 node scheduled for 2026, N2P. So assuming all schedules hit as they should, Intel will have a very good node 18A with both these innovations in the market. Just as important as all this impressive manufacturing is also the design aspect. Existing power delivery networks for ICs are incredibly complicated as they are now. BSPN presents a tricky new proposition for designers like Intel and TSMC's customers. They have to port over all their networks and redesign them to work just as well as they have before. This is a massive EDA design challenge. But the benefits are immense. Just as these backside techniques open the backside door, to incredible 3D stacking benefits for image sensors, it poises to do the same for digital logic. This is not a one-time boost. This is a trend that will last. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.